Algebra in the German school during Renaissance. Johann Widmann on 1460. At the University of Leipzig, he wrote the known-out Allen Kaufmann-Chaplin used plus and minus first time in print, where this was encouraged by the use of plus and minus symbols. Adam Rees on 1492 to 1559. He wrote the Dikos on 1524, the influential arithmetic and algebra text. In Germany, the term das Mädchen as Adam Rees still survives as the German children know its meaning, word that gives according to Adam Rees when doing arithmetic. He also wrote arithmetic textbooks, namely the Rechnung auf der Grenchen und Federn in Saal, and also the Mass und Gewicht auf allerlei Handerung, where the textbooks contains addition, subtraction, multiplication, and division. It was remarkable because at that time, division could not only be learned at the university, because even scientists did not know how to divide. That's why Adam Rees offered methods derived from the abacus, those derived from India. Christoph Rodolph on 1500 to 1545. In 1525, he composed a book on algebra entitled Dikos, which he uses decimal fraction and modern notations of roots, and also a term which can be traced to its Italian origin cosa, meaning thing or unknown. Algebra was first conceived as a mathematical discipline of finding in a unknowns in a problem situation. Peter Appian. He wrote Rechnung on 1527. In this, we can see the Pascal's Rians appears on its title page. Michael Stiefel on 1487 to 1567. He was a Lutheran preacher, and for the meantime, he was a professor at Jena. He wrote the Arithmetica Integra on 1544. There are some features of Michael Stiefel in his term, namely the use of plus and minus, significant for treatment of negative numbers, radicals, and powers, using negative coefficients and the irrationals. All the many cases of quadratics were reduced to just one, but no negative roots are allowed. Now let's proceed on algebra in English school during Renaissance. Robert Ricordi on 1510 to 1558. He was an Englishman who virtually established the English School of Mathematics and first introduced algebra into England. Ricordi is best known for inventing the equals symbols, which appears in his book The Wheatstone of Wheat in 1557. Ricordi was educated at Oxford and Cambridge. He became physician to King Edward VI and Queen Mary. He served for a time in Ireland as comptroller of mines and arithmetic. He wrote many textbooks. For example, The Grundy of Artists in 1540 was a very commercial arithmetic book teaching the perfect work and practice of arithmetic in Ricordi's own words. The book discusses operation with Arabic numerals, computation with counters, proportion, the rule of three, and the fractions. In 1551, Ricordi wrote Pathway to Knowledge, which some consider as a bridge version of Euclid's Elements. It is only one of his books not written in the form of a dialogue between master and scholar. The equal symbols appears in Ricordi's books The Wheatstone of Wright, published in 1557. He justifies two parallel line segments because no way two times can be more equal. The symbol equal was not immediately popular. The symbol minus was used by some and AA or OA from the word equalis, meaning equal, was widely used into the 70s. Ricordi died in King's Beach prison in Southmark, which he was committed for death. Although no official record remains of other crimes, some historians think he was guilty of much more serious offenses. There was a following notation: P for plus, M minus, which was found by Chekrit and Pacioli. The unknown sources: the ris from Latin, jus from French, cosa from Italian, cos from Germany. Plus and minus was found by Widmann on 1490. R squared square root was found by Rudolph on 1525, and the equal symbols was found by Ricordi in 1557. Now let's move on to the solution of the cubic and quartic equation. Mathematicians had been working toward a solution for at least 15 years. Solving the cubic was one of the significant feats of the next few centuries that would unshackle the European mathematicians from their Greek heritage. Iskyphon Del Fierro on 1465 to 1525. He was a collagio of Pacioli. Del Ferro is the first to solve the cubic equations by radicals. He only solved one of the two cases. The fact that zero and negative numbers were not in use made many distinct cases. Niccolo Fontana Tartaglia on 50s to 1557. He was famed for his algebraic solution of cubic equation, which was published in Cardan's Ars Magna. During the French sack of Brescia in 1512, his jaws and palate were clipped by a sabre. Tartaglia was self-taught in mathematics, but having an extraordinary ability, was able to earn his living teaching at Verona and Venice in 1534. Tartaglia wrote the Nova Scientia in 1537, a new science. On the application of mathematics to artillery fire, he described new ballistic methods and instruments, including the first firing tables. Tartaglia also wrote a popular arithmetic text, Trattato de Numeris Maesure, in 3 volumes, on 1556 to 1560, treatise on numbers and measures, an encyclopedic treatment of elementary mathematics. He was also the first Italian translator and publisher of Euclid's Elements in 1543. He has a lot of published in Latin editions of Archimedes' works. Girolamo Cardano on 1501 to 1576. Cardano was famed for his work Ars Magna, which was wrote in 1545, which was the first Latin treatise devoted solely to algebra. He gave the methods of solution of the cubic and quartic equation, which he had learnt from Tartaglia. Girolamo Cardano's name was Cardan in Latin in English. He is sometimes known as Jerome Cardan. Cardano lectured and wrote about mathematics, medicine, astronomy, astrology, alchemy, and physics. Cardano Ars Magna made known the solution of the cubic by radicals and the solution of the quartic by radicals. These were proved by Tartaglia and Ferrari, respectively. The Ars Magna was the first computation with complex numbers, although Cardano did not properly understand about it. The work was written completely in a rhetorical style. Symbolism have not yet been invented. The Ars Magna was also known Artis Magnae. Ferrari Lodovico on 1522 to 1565. He found a method of solving the quartic equation. He was sent as a refugee to Milan, where he joined the house of Girolamo Cardano in 1536. Cardano introduced him to Latin, Greek, and mathematics, not the normal course of training for an errand boy. In 1540, he was appointed by Ferrante Gonzaga, the governor of Milan, public lecturer in mathematics in Milan. He was succeeded as public mathematics lecturer in Milan. In this capacity, he gave lessons on the geography of Ptolemy. He collaborated with Cardano in research on the cubic and quartic equations, the result of which were published in the Ars Magna on 1545. By all accounts, it was Ferrari who found the methods of solving the quartic equation. Ferrari brought the publication of Ars Magna into a well-documented controversy with Tartaglia over the solution of the cubic equation. The solution of the cubic. Solving cubic was one of the significant feats of the next few centuries that would unshackle the European mathematics from their Greek heritage. The cast of characters was singularly unsavory, with lust and genius commingled with public disputes and contests and with broken promises. The cast of the solution of the cubic: Hieronymo Cardano, which found the Ars Magna; Niccolo Tartaglia; Ludovico Ferrari. Now, transform ex cubed plus bx raised to the power of 2 plus cx equals d into x raised to the power of 3 plus px equals q. First, dividing by a and then using the transformations x equals y plus b and then y equals x. Next, define u and v by u minus v equals x and uv equals 1 over 3 p. This gives u minus v raised to the power of 3 plus p multiplied to u minus v equals q. The result was u raised to the power of 3 minus 3u raised to the power of 3v plus 3uv raised to the power of 2 minus v raised to the power of 3 plus p multiplied to u minus v equals q. U raised to the power of 3 minus v raised to the power of 3 minus 3uv multiplied to u minus v plus p multiplied to u minus v equals q. Now, u raised to the power of 3 minus v raised to the power of 3 equals q. Using v equals p over 3u, substitute to get u raised to the power of 3 minus p over 3 raised to the power of 3 over u raised to the power of 3 equals q. U raised to the power of 6 equals, minus qu raised to the power of 3 equals p over 3 raised to the power of 3. U raised to the power of 3 multiplied again to 2 minus q multiplied to u raised to the power of 3 equals p over 3 raised to the power of 3. Now, solve for u. U equals q positive negative square root of q squared plus 4 times p over 3 raised to the power of 3 all over 2 and then multiplied 1 over 3. And then for v, finally for x, now compute v equals p over 3u and then compute x equals u minus v. After some simplification, we can obtain the form given by Cardano, namely x equals the cube root of the square root of p over 3 raised to the power of 3 plus q over 2 raised to the power of 2 plus q over 2 minus the cube root of the square root of p over 3 raised to the power of 2 plus q over 2 raised to the power of 2 minus q over 2. However, his solution is rhetorical. Example number 1. Solve x cubed plus 3x equals 4. Solution. X equals the square root of 1 plus 4 plus 2 multiplied to the power of 1 over 3 minus the square root of 1 plus 4 minus 2 multiplied to the power of 1 over 3 equals the square root of 5 plus 2 raised to the power of 1 over 3 minus square root of 5 minus 2 multiplied to the power of 1 over 3 equals 1. Example number 2. In Ars Magna, we find x cubed equals 15x plus 4. The solution here by the formula is x equals the cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of negative 121. Cardano knew there was no square root of negative 121 and he knew x equals 4 was a solution. He did not know how to proceed. He referred to such square roots as the sophists and thought taking square roots of negative numbers was as subtle as it is useless. Solution of the quartic equation. As explained in the preceding section, we may start with a depressed quartic equation. Y raised to the power of 4 plus py raised to the power of 2 plus qy plus r equals 0. This depressed quartic can be solved by means of a method discovered by Ludovico Ferrari. The depressed equation may be written. This is easily verified by expanding the square and regrouping all terms on left-hand side as y squared plus p over 2 raised to the power of 2 equals negative qy minus r plus p raised to the power of 2 over 4. Then we introduce a variable m into the factor in the left-hand side by adding 2y squared m plus pm plus m squared to both sides. After regrouping the coefficients of the power of y on the right-hand side, this gives the equation y squared plus p over 2 plus m all over raised to the power of 2 equals 2my squared minus qy plus m squared plus mp plus p squared over 4 minus r, which is equivalent to the original equation whichever value is given to m. As the value of m may be arbitrarily chosen, we will choose it in order to complete the square on the right-hand side. This implies that the discriminant in y of this quadratic equation is 0, that is, m is a root of the equation. Negative q squared minus 4 multiplied to 2m, that multiply also m squared plus pm plus p squared over 4 minus r equals 0, which may be written as 8m cubed plus 8pm squared plus 2p squared minus each r multiplied to m minus q squared equals 0. This is the resolvent cubic of the quartic equation. The value of m may thus be obtained from Cardano's formula when m is a root of this equation. The right-hand side of the equation is the square. The square root of 2my minus q over 2 square root of 2m all over raised to the power of 2. However, this induces a division by 0. If m equals 0, this implies q equals 0, and thus that the first equation is b-quadratic and may be solved by an easier method. Now, if m is a root of the cubic equation such that m is not equal to 0, equation 1 becomes y squared plus p over 2 plus m raised to the power of 2 equals y the square root of 2m minus q over 2 square root of 2m all over raised to the power of 2. This equation is of the form m squared equals n squared, which can be rearranged as m squared minus n squared equals 0, or mn multiplied to mn equals 0. Therefore, equation 1 may be written as y squared plus p over 2 plus m plus the square root of 2m minus q over 2 square root of 2m multiplied to y squared plus p over 2 plus m minus square root of 2my plus q over 2 square root of 2m equals 0. This equation is easily solved by applying to each factor the quadratic formula. Solving them, we may write the root as you can see on this picture. This equation is easily solved by applying to each factor the quadratic formula. Solving them, we may write the roots as y is equal to plus positive or negative 1 square root of 2m, positive negative square root of negative 2p plus 2m, positive negative square root of 2q over square root of m all over 2, where positive negative 1 and positive negative 2 denote either plus or minus, as the two occurrences of positive minus 1 or negative 1 must denote the same sign. This leaves 4 possibilities, 1 for each root. Therefore, the solution of the original quartic equation are x equals negative a 3 over 4a4 plus positive or negative 1 square root of 2m, positive or negative 2 square root of negative 2p plus 2m, positive negative 1 square root of 2q over square root of m all over 2. A comparison with the general formula above shows that square root of 2m equals 2s.